All right, let's give an example problem here. How about problem 14? This is a linear transformation of vector space problem. Let V and W be vector spaces and T, a map from V to W, be a linear transformation. Prove that T is 1 to 1 if and only if T carries linearly independent subsets of V onto linearly independent subsets of W. So a little scratch work. I always sort of start. Okay, this is an if and only if proof, so we're going to start one direction, but then we'll go the other way. So I'm going to sort of start out assuming T is 1 to 1. That's what I have. What do I want? What I want at the end is I'm going to want that if I had some set V1 to Vn, a subset of V that is linearly independent, that implies that beta, the set of T V1 to T Vn, is linearly independent, and that's a subset of W. Now, I notate that finitely, and I'm going to do that throughout, but you can actually, if you want to, you can say VI, I in an infinite set like that, and you can do infinite linearly independent sets throughout the proof. But okay, so I'm starting with this. What does that actually mean? What do I get? What leverage do I have? Well, this is a fact. Essentially, if two things have the same output, if T of X equals T of Y, that means X equals Y. So this is the fact I'm going to be using as I'm going this direction. It's going to be the thing I'm trying to prove when I go backwards. Okay, and to prove an implication, I'm going to assume this piece. So going forward, I'm going to assume this, I'm going to assume that, and I'm going to try and get to this. Okay, so let's see how we can do on a proof like that. Alrighty, so what are we going to say? We're going to say let T be 1 to 1. Choose alpha equal to V1 to Vn, a linearly independent subset of V. We need to show that beta equals to the set T of V1 up to T of Vn is linearly independent. Okay, when we get that, we're set. How do you show something is linearly independent? Well, saying something is linearly independent is we've got to choose coefficients A1 up to AN in the field such that A T V1, A1 T V1 up to A N T Vn equals 0. And to show that it's linearly independent, I've got to show that all the AIs are 0. Well, this is just a classic linear transformation setup. What do you do when you have all these things that are linear? Well, the answer is, by linearity, you put them together. I'll do it in 2 steps right now, although usually we'll do it in 1. T of A1 V1, that by scalar, the linearity across scalars, that's equal to that, dot, dot, dot. T AN Vn equals 0. And T of A1 V1 all the way to AN Vn equals 0. But also, I know another thing that maps to 0. t of 0 equals 0. So since t is 1 to 1, remember what that meant. Remember with our scratch work, if we have two things that are equal, we get a1 v1 out to an vn equal to 0. Well, what else did we get? We chose these to be a linearly independent subset. Also by linear independence of alpha, a1 equals out to an equals 0. Okay, but that's really what we were trying to get up here. Therefore, beta is linear independence. You can pause that and think about it more if you want to. But we've gotten one direction of this proof. Now we need to go the other direction, okay? The other direction, now assume for any linearly independent alpha v1 to vn in any linearly independent set in V, beta equal to t of v1 out to t of vn is linearly independent. Okay, so often when you're dealing with linear independence, implicitly, the best thing to work with is a basis, because bases are linearly independent, and they span everything. So that's kind of where we're going to go with this proof. But let's think about what we're trying to get to. Okay, we've got this. We need to show that t is 1 to 1. How do you show something's 1 to 1? Choose x and y in the domain such that t of x equals t of y. So to be 1 to 1, we need to show, all we really need to show is x equals y. Well, I don't know how to write, I don't know what to do with x and y, but I'd like to work with something that's linearly independent. Let's rewrite these in terms of a basis, right? So choose a basis of phi, and for convenience, I'll use this same notation. Alpha equals v1 to vn, okay? So now remember what we get for free in our hip pocket is, and you don't have to say this, but so beta is linearly independent, right? This setup here is linearly independent. We're gonna have to use that somehow to get back, right? Okay, so this is a basis. Since alpha is a basis, choose a1 to an, b1 to bn coefficients such that x equals a1 v1 out to an vn and y equals b1 v1 plus bn vn. If you had infinite sets here, notice everything can be written as a finite linear combination of those, but your indices might be different finite numbers, and you have to work just a little bit harder to put those two finite sets together, but two finite sets is still finite. So we've got this. What are we trying to do? We're trying to show x equals y. What do we have? We have t of x equals t of y, right? So we know t of x, that's t of a1 v1 out to an vn, equals t of b1 v1 out to bn vn, right? This is t of x equals t of y. Now this is a pretty classic linear transformation. Look, what do you do when you have a linear combination inside a linear transformation? See here, we got to a linear combination inside a linear transformation. Here we're getting from that. So what do I get? I get a1 t of v1 plus, breaking it out, an t of vn equals b1 t of v1 all the way out, breaking it apart with linearity to here. Now, these are elements of W, so I can put them all over on one side and I can gather them. This is t of v1 is one element of W. I have a1 over here, I have b1 over here. So another way to write this is I have a1 minus b1 tv1s if I subtract this over to the other side. And I can do that for the same for all of them, an minus bn tvn, and if I subtract every term over here, I get 0. Oh, so I have a linear combination of the tvn's that equals 0. So by assumption, remember we knew we were going to come back to this, the betas are linearly independent. This is the set of the betas. a1 minus b1 equals 0, as do all the others. an minus bn equals 0. Well, if those differences equal 0, that means a1 equals b1 out to an equals bn. In other words, x equals y, right? All of the coefficients in this basis are exactly the same, so they're exactly the same element. Therefore, t is 1 to 1. Now, if you want to, you could go back and you could make these infinite indices, I in I and so on, but then these linear combinations would still be finite things.